Example 6. A shiny new phone is worth $1,200. You probably paid a lot more for it, but maybe that's what it's worth. It loses 13% of its value every year. Probably more than that. How much will it be worth after 8 years? So, we don't know what the final amount is going to be. The initial amount was $1,200. Now the growth, though, in this case, it's losing 13% of its value. So in this case, this is a decay. And instead of being plus, it's actually going to be negative 13%, which is going to be negative 0.13. And the number of times it grows is going to be, well, it's that much per year, so that one's pretty straightforward. So the amount is going to be, so remember, A naught is equal to 1 plus g to the n. So it's going to be 1,200, but the g here is now negative 1.3, which means it's going to be 1,200 times 0.87 to the 8th. It's going to be worth 87% of its value 8 times. That's what it means when you're losing 13% every year. So 0.87 to the 8 times 1,200. And after 8 years, it is worth $393.85. And that's probably an overestimation. Probably worth a lot less than that. Okay. Number 7. The number of ants in a colony doubles every 3 years. If there were 73 ants at first, how many would there be after 24 years? I'm going to guess probably quite a few. So the final amount, we don't know. We started off with 73. Now the growth. If we're doubling, what that means is that we are growing by 100%. So we have, our growth is actually 100%, which if we turn into a decimal is 1. You could grow by more than 100%. You could grow by 200%, that would be tripling. And 300% would be quadrupling, I guess. Kind of weird. Now, the number of times we grow, so it's 24 years, but this growth happens every 3 years. So it's 24 years and divided by 3 years per growth. So it's going to happen 8 times. So we're going to grow 8 times. So putting that together, we have A is A naught 1 plus g to the n. So A is going to be 73, 1 plus 1. And the n, for a variety of reasons, I'm going to write it like this. I'm going to write it as 24 over 3. It is 8, but I'm writing it as 24 over 3. So A equals 73 times 2 to the power of 24 over 3, which in this case would be, so now I'll put in 8. So 2 to the 8, 2 to the 8, 2 to the 6 times 73. And we're going to have 18,688 ants. So we're going to have, we'll have 18,688 ants crawling around after 24 years, starting with only 73. And that's doubling every 3 years. It might even double faster than that. This is a special type of problem. This is a special type of problem. We're going to call these type of problems doubling problems. So this is a doubling problem. And what we're going to do with the doubling problems is we're going to make a formula for it. So we're going to have a doubling formula. And we're going to define some variables. So I'm going to say that A is the final amount, A naught is the starting amount, T is going to be how much time has passed, and D is going to be the doubling time, which is how long it takes to double once. So that's the time to double once. And if we look at it, what we could see is that the formula would be, well, let's get a good pen for this one. That's a good formula. So it's going to be A equals, oops, sorry. So A equals A naught. And since it's doubling, it's always going to be a 2. And then how do we figure out the n? It's going to be the time, elapsed time, divided by the doubling time. And this is a formula for doubling time. You don't have to use this formula. We were able to do the problem before just with the general formula. But if you have a doubling problem, then you could use the doubling formula with those variables.